Let's talk about common source amplifiers. In this video, I'm only going to be using in-channel enhancement mode MOSFETs. Enhancement mode basically means you need to apply a positive voltage at the gate in order to turn the device on. Let me show you an example circuit. This is a common source amplifier. We have a signal over here that we supposedly want to amplify, and that flows through the circuit and drives a load resistor over here at the right. The reason why this is called a common source amplifier is because the source here is not connected to either the signal or the load. The reason why we have these four resistors around the MOSFET is because we need to make sure that the transistor is in the saturation region all the time. We don't want the transistor to either turn fully off or fully on, which would correspond to the cutoff or the ohmic regions. We're trying to make here a linear amplifier, in other words. In order to make sure that the transistor is in saturation, we basically want the voltages up here at the top to be high, the voltage here in the middle to be a medium range voltage, and the voltages down here at the bottom to be ground. Basically, high, medium, low at the drain, gate, and source. Something to note about MOSFET amplifiers compared to bipolar transistor amplifiers is that the input impedance, or the impedance looking into the gate, tends to be very high. Unlike the situation in a bipolar transistor, when you need to be careful not to make R1 and R2 too high. In a MOSFET, because there's very little current into the gate, you don't have to worry about screwing up your voltage divider if you make R1 and R2 a larger number, like in the mega ohm range. Now let's talk about the gain of a common source amplifier. A gain of a common source is basically the resistors looking up from the drain divided by the resistances looking down from the source. If you've watched my videos on bipolar transistors, you might notice that it's the same formula. But let me prove it to you, and then we'll do some example circuits. Let's start by calculating the voltage right here at the gate. And we're first going to be doing a DC analysis. So I'm not going to worry about the signal over here at the left, and later I'm not going to worry about the load resistor R sub L. The voltage at the gate is just a fraction of the power supply voltage. We have a voltage divider here set up by resistors R1 and R2. Now let's find the voltage at the source of the transistor. If it were a bipolar transistor, I would just subtract 0.7 volts. But to turn on a MOSFET, you have to exceed the threshold voltage. So here, we're going to be a threshold voltage down from the gate. The threshold voltage is different for every transistor, and even if you have the same transistor type, from component to component, you might have different threshold voltages. So we could call the threshold voltage a bit of a fuzzy number. Quite often in circuit design, we're not sure what that threshold is going to be exactly, so we have to make sure that our circuit can accommodate a range of threshold voltages. Fortunately, it doesn't make a big difference for the gain, as you'll see in a moment. Let's now find the source current, or the current down here through the source. We have a slight nomenclature problem because we have the source, meaning the signal, and we also have the source of the transistor. So I'll try to use source to refer to the source of the transistor, and I'll try to use signal at the input. Since we know the voltage at the source, we just need to divide it by the source resistance in order to find the current. That same current is going to be flowing through the drain. For the moment, I'm going to neglect the load resistor because that's an AC component, and we're doing a DC analysis. The leakage, or the contribution from the gate, is so tiny that we can always ignore it when we're doing MOSFET circuit analysis. Since the source current is equal to the drain current, I'm going to go ahead and find the drain voltage by applying Ohm's law across resistor RD. The voltage here is going to be my power supply dropped by the current times the resistance. We have the current right here, so I just need to multiply it times the resistance R sub D. All right, let's now include the contribution from our signal, The signal over here is going to be an AC source, and the amplitude might drop a little bit across the signal resistor R sig. Let's say that the purely AC voltage at this point in the circuit is called little v sub g. I've used a small letter because that's going to be an AC voltage. As long as our capacitor here is large enough, that AC voltage will go right through it and add to the voltage that we have at the gate. Let's go ahead and write in our AC contribution to our equation. Just to make things clear, we know that the voltage at the gate has a DC component added to an AC component. Let's propagate this extra term through the rest of our equations. We now have a full expression for our drain voltage, including both AC and DC components, but right next to our drain we have a capacitor which is going to block all of the DC components. So let's go ahead and identify the AC portion of our drain voltage. It's just minus the drain resistor over the source resistor, and you can already see that this is going to be the form of gain. One thing to notice is that we've neglected the load resistor in this analysis, so we'll have to fix that in just a moment. We'll make a note of it for the time being. We'll just say that the load resistor is large. If it's large, then there's not very much current going through it. Let's create an AC equivalent circuit, because we're also going to have a voltage divider from the signal to the gate. Let's start over at the left side with our signal, V sub S. The signal then sees resistor R sig, and here we have our gate voltage. The signal will go right through that capacitor, assuming it's large enough, and it will see the input impedance to this circuit. The input impedance is just going to be given by R1 in parallel with R2. Of course, we have a third branch going into the gate, but that's typically a huge resistance that we can neglect. Over here on the right, we have drain current, and I'll call that little I sub d. The transistor pretty much behaves like a current source at this point, so let's label it I sub d, and it pulls current down through resistor R sub d. If we look over here at the left, we can identify the AC portion of the drain current, or equivalently the AC portion of the source current. Let's make a note of it. It's just gate voltage divided by the source resistance. From this AC equivalent circuit, we can come up with an equation for the gain. Let's now calculate the gain, and we'll recall that this is the situation if the load resistance is large. We'll label our load voltage here. We can split this gain into two parts. We have the gate voltage over the signal voltage and the load voltage over the gate voltage. For the first term, we can identify a voltage divider over here at the left side. From this equation, we can just apply Ohm's law across resistor RD. V equals IR, and the current's flowing up instead of down. For ID, we'll plug in this term, and we now have our required ratio. Let's now think about what would happen when we include the load resistor in the analysis. We can just add it into our AC circuit and see what happens. The drain current is the same, but everywhere I have written R sub D, I should replace it with R sub D in parallel with R sub L. So we can add it here and here. In our calculation of the gain, we can also add it up here, and we can get rid of that condition finally. So now we have a more or less complete expression for the gain. We have an input voltage divider, and then a gain segment that's just all of the resistors at the drain divided by all of the resistances at the source. There's another way to write this term, and to do it, I'm going to expand the two resistors that are in parallel. You might recall that resistors in parallel are just multiplied in the numerator and added in the denominator. This expression makes it very clear that if the load resistor is large, then the fraction over here at the right becomes very close to 1, and it can be neglected. This new expression will allow us to draw an alternative AC equivalent circuit. In that circuit, we'll have an input voltage divider, a voltage source, and an output voltage divider. The input voltage divider is going to be the same as our original circuit. we have our signal resistance, gate voltage, and input impedance to the amplifier. However, now instead of drawing a current source, I'm going to draw a voltage source. That voltage source will have a gain of minus RD over R source. Then we'll have an output voltage divider, and this circuit gives this equation when you analyze it. I tend to like this alternative AC equivalent circuit just a little bit better because I think it's easier to remember and it's easier to apply when you have multi-stage amplifiers. We can look back at our original circuit and very easily identify the output impedance. This corresponds to the output impedance of this circuit as well. One thing to keep in mind is that all of this AC analysis is fine and well, but the transistor has to be in saturation, so the DC bias had to have been accurate from the beginning. Let's work an example together. We're going to be estimating the gain if we have a threshold voltage around 2 volts. Just by inspection, we can see that the gain is going to be -2 if I take this resistance divided by this resistance, and that it's going to be reduced a bit by some voltage divider. So I expect a gain somewhere between -1 and -2. Let's see how it works out. First, let's do a DC analysis to make sure that this transistor is in saturation. Let's find the gate voltage first. So we have a voltage divider here set up by these two resistors, 1 mega ohm and 1.5 mega ohm. And when applied to our 10 volt power supply, it gives us 4 volts. Fine. Label it here. Now let's find our source voltage. And we're going to be dealing again with this fuzzy number, or the threshold voltage. Of course, it might not always be 2 volts. It might vary a little bit with the drain current, and it might vary a little bit from transistor to transistor. Let's nonetheless use it to estimate a source current. Using Ohm's law across the 1 kilo ohm resistor, we can see that it's just going to be 2 milliamps. That same 2 milliamps is going to be flowing through the drain resistor, and we can use it to find the drain voltage. So the drain voltage is going to be a little bit lower than 10 volts. We only have to find the voltage drop across that resistor. Altogether, that gives us 6 volts. High, medium, and low saturation. That's what we want for a MOSFET. So we can go ahead and proceed to the AC analysis. Let's draw an AC equivalent circuit. So we have our signal. We then have a 1 kilo ohm signal impedance. Let's assume that our capacitors are large, in which case the signal is not attenuated at all through the capacitor. And we then have our input impedance. So the input impedance here is just 1.5 in parallel with 1. That works out to be 600 kilo ohms. So at this point, we have our AC gate voltage and a 600 kilo ohm input impedance. For a common source amplifier, the gain is going to be given by this resistance looking upwards divided by this resistance looking downwards. So we have 2 kilo ohms up there on the top and 1 kilo ohm down there on the bottom. The output impedance looking back is just 2 kilo ohms. We can neglect the impedance looking down the drain as being high, just like we could with a bipolar transistor looking down into the collector. Here's the output impedance, 2 kilo ohms as we just calculated, and finally we have our 10 kilo ohm load. Let's use this circuit to find our overall gain, which is given by 3 components. We have an input voltage divider, a gain segment, and an output voltage divider. There's our first, there's our second, and here's our third. Working that out, we come up with an estimate of the gain at negative 1.67. I simulated it on LT Spice with a 2N 7002 transistor, and it worked out to be minus 1.53. As you can see, our simple model of a MOSFET is not quite as accurate as our simple model was for the bipolar transistor. Nonetheless, we're within a few percent for our gain calculation. Let's work another example. The only thing different about example 2 compared to example 1 is the presence of this 600 ohm resistor attached to the source. The DC conditions, therefore, are unchanged, so this transistor is still in saturation, and I'm not going to bother with the DC analysis. Although the 600 ohm resistor doesn't change the DC analysis, you might take note that the AC current that passes through the source is now going to be divided across two resistors. In other words, the AC signal sees two resistors down there in parallel with one another. It's going to give a smaller equivalent source resistance, and it's going to increase the gain accordingly. Let's see how it works out in the AC equivalent circuit. We have our signal, our 1 kilo ohm signal impedance, and our input impedance, which we calculated before as 600 kilo ohms. We now have our voltage source, and if this is a common source amplifier, which it is, then the gain is given by this resistance looking up the drain divided by this resistance looking down from the source. So we have 2 kilo ohms on the top and 1 kilo ohm in parallel with 600 ohms down there on the bottom. Our output impedance is 2 kilo ohms, so let's go ahead and draw that as well. And then finally, our load is 10 kilo ohms. Our overall circuit gain has three different components. We have an input voltage divider, a gain segment, and an output voltage divider. Sometimes with MOSFET circuits, I also include a fourth term here, and I call it a fudge factor, and usually my fudge factor is about 0.9. We'll see how it works out with and without the fudge factor. The first three terms together give minus 4.44. If I include a fudge factor of 0.9, then my overall gain becomes about minus 4. I simulated it on LT Spice with the 2N7002 MOSFET, and the gain worked out to minus 3.7. So even with the fudge factor, we're off a little bit for the gain. You might have started to notice a general theme. It's a little bit more difficult to predict the gain for a MOSFET amplifier as it is for a bipolar transistor amplifier. Let's work a third example, and we're going to again assume that the capacitors are large. The resistances are slightly different than they were in the previous example, so we're going to have to start off with a DC analysis. First, let's find the DC gate voltage. In this case, it's just a simple voltage divider. We have 12 volts divided across two 1 mega ohm resistors, so we can see by inspection that we're going to get 6 volts there at the gate. We can go ahead and write it on our circuit. If I would work this problem in the same way I worked the previous two examples, my next step would be to just say that our source voltage is about a threshold voltage below our gate voltage, or I would say that our source voltage here is about 4 volts. In this case, though, we've been given a curve that relates the drain current to the gate source voltage. So let's try to be a little bit more accurate this time and get a feel for where the transistor is actually operating on this curve. First, I'm going to label the drain current I sub D on my circuit diagram. Let's call this voltage the source voltage. And through Ohm's law, I know that the source voltage is the drain current times 500 ohms. I know that my gate voltage is going to be VGS higher than my source voltage. I'm not going to assume that it's exactly at threshold in this problem because I'm trying to be a little bit more accurate now. We can substitute in for my source voltage. And I now want to rewrite this equation so that the drain current is on the left. I already know my gate voltage, it's 6 volts. I'm going to rewrite this one more time, but I'm going to assume that the drain current is in milliamps. I'm doing that because the graph over here is in milliamps, and I'm going to use the graph in just a moment. This means we need to multiply everything over here times 1,000, so that gives me minus 2, and this gives me 12 after I plug in 6 volts for my gate voltage. This is just the equation of a line, and it basically just describes Ohm's law across the 500 ohm resistor. But this line relates the drain current to the gate source voltage, so I can superimpose it upon the transistor's operating curve that we already have plotted. We can see where the curves intersect, and that's going to be the operating point of our transistor. We might recall that the equation that describes this operating curve for a MOSFET in saturation is given by the following. We can see that our operating point is nearly 6 milliamps when the gate source voltage is about 3. Let's plug those numbers into this equation. We can also take note that our threshold voltage is 2, and V squared here is just a label, volt squared. This equation can be solved for K, so K is just 6 milliamps per volt squared. Having identified a K, I can now write an equation that relates drain current to the gate source voltage. All we've done at this point is find an algebraic expression for this blue curve. Let's now think about what happens when we have an AC signal that's imposed upon this curve at the gate. It's going to cause the gate source voltage to swing around a little bit, which will then cause the drain current to change. In other words, an AC voltage applied at the gate is going to cause us to move up and down the blue curve. What I'm interested in knowing is the slope of this line at this operating point. So we're going to have some change of the gate source voltage. We could call it delta VGS. That's the input, and then the output will be some change in the drain current. Let me call that delta I sub D. We could get the slope of the line graphically if we wanted to, but we can also use calculus to get it. Let's take the derivative of the drain current with respect to the gate source voltage. It's going to be 2K VGS minus VTH. So here it gives us 12, and our gate source voltage is 3. So let's plug in 3. And the slope is just 12, the units here being milliamps per volt. The slope of that line, as you might recall from a previous video, is just the transconductance. It's usually given the symbol G sub M. What I now want to do is draw our AC equivalent circuit and see how we can find the gain. We'll start with our signal voltage, and then we have a 1 kilo ohm signal impedance here. We then have a large input impedance of 1 mega ohm in parallel with 1 mega ohm, so that's going to give me 500 kilo ohms. Not much of a voltage divider there at the input side. Let's now think about our AC output voltage. At this point in the circuit, we have the MOSFET, which functions as a current source, sucking current out of that point. So let's draw the MOSFET as a current source with a current of I sub D, the drain current. Now, what is that drain current? Well, I'm only interested in the AC portion of it, and we already know from our operating curve where this transistor is operating. We have an equation that relates small changes in the drain current to small changes in the gate source voltage. So let's go ahead and write what we know. It's just our gate source voltage times our transconductance. Now let's carry on with our circuit. The AC signal sees two resistors, 700 and 10 kilo ohm. Let's label this as our output voltage. From our circuit, the output voltage is going to equal the drain current times these two resistors in parallel. We can substitute for our drain current. And because our source has a large capacitor attached to it, it's basically grounded, and our AC gate source voltage is basically just our AC gate voltage. Our AC gate voltage is shown right here in our AC equivalent circuit. Let's substitute in for our AC gate voltage using our input voltage divider. There's our gate voltage, and now we have the other terms in this equation. Let's take these two resistors in parallel, and let's rewrite this expression. Multiplied in the top, added on the bottom. Now I'm going to take this Gm, and I'm going to do something that you might think is a little bit strange. I'm going to put it in the denominator as 1 over Gm, and then write the rest of this expression. The reason I've done it is so that we can treat our MOSFET analysis in an equivalent or an analogous way as we did with the bipolar transistors. If we look back at example 2 and example 1, our strategy for finding the AC gain was to take the resistors up here at the drain and divide them by the resistors down here at the source. Of course, we're going to have trouble doing that here with this MOSFET because it looks like we have an AC ground and we would have a divide by zero operation. And mathematically, we can't do that. So the question is then, how do we find the gain? Well, if you look at the form of this expression, we notice that the transconductance has units of inverse ohms, or in this case, 1 over
inverse kiloohms.
The transconductance is just the inverse of a resistance. So down here in the denominator, we have some kind of a resistance. Let's call it little rs. And if we look back at our circuit, we can kind of imagine that the MOSFET has a little R sub s right here, and it tends to be a small number, but we can't neglect it if we're grounding the source. So let's come up with a revised strategy for finding the gain of MOSFET circuits. If you see a common source amplifier and you have the source grounded through a large capacitor, the gain segment of that amplifier can be approximated by this resistance divided by this resistance, where you imagine a little source resistance right there. That's just the inverse of the transconductance. Now, the transconductance is not always easy to get. If you have the operating curves of the transistor, you can extract it like we did here. But if you have a data sheet, you can also sometimes just read it off the data sheet or come up with some kind of estimate for it. That allows us to revise our AC circuit a little bit. So rather than write it the way I have, let's redraw this current source as a voltage source. Let's use just the load resistor over here at the output side and reflect our equation. So the output impedance here is 700 ohms, and that's now properly reflected in our AC equivalent circuit as well. Let's replace our current source with the voltage source. If you like the current source, you can keep it there. These methods are equivalent, but I like voltage sources. And when I see a common source amplifier, I'm just going to remember that the gain here is given by this resistance, which is 700, divided by all of these resistances down here, which in this case is 1 over Gm. So we need to put 1/12 down there in the denominator. The gain is then given by an input voltage divider. We've already written it here. A gain segment, as we've noted here, and an output voltage divider, as we've noted down over here. So the net gain is minus 7.8 when you plug in all the numbers. You might recall that when we arranged circuits similarly using common emitter amplifiers, the gain tended to be much higher. And that's because with a bipolar transistor, the emitter resistance tends to be a small number compared to the inverse transconductance that you would get with MOSFETs. That means the maximum possible gain that you can get from one of these MOSFET circuits tends to be limited relative to what you can get with bipolar transistor. Let's now take a look at a typical data sheet for one of these MOSFETs. We're looking at this data sheet now because I'm about to work another example, and I'm going to show you how you can extract the transconductance from one of these data sheets without having to do a lot of work. The data sheet shows us the forward transconductance, but for all of these examples here, the forward transconductance was measured at a drain current of 200 milliamps. We know that there's quite a possible range here in the transconductance, but let's just take the typical values as a starting point. The typical value of the transconductance for the 2N7002 transistor is 320 millisiemens. Where's that on our operating curve? Well, 200 milliamps is pretty low on this curve. So what that transconductance means is that we have a particular slope of that line. The slope is 320 millisiemens. Now let's think about what would happen if we operate the transistor at an even lower drain current. That's what I'm going to work here in a moment in the next example. We're going to be operating a transistor at 100 milliamp drain current. Knowing that we're going to operate a transistor at this lower drain current, can we guess what the transconductance would be for the transistor? Well, look at what happens to the slope if we lower down our drain current a little bit. Is the slope going to increase or decrease? Well, that curve is starting to slope at a more shallower angle. So my guess is that the transconductance is going to decrease. I don't know how much, but I'm just going to make a guess. Let's say 200 millisiemens. At least that will give us some way to estimate the gain without doing a lot of work. The datasheet also tells us that the transistor can dissipate up to about 370 milliwatts of power, but I'm not showing that part of the datasheet here. We'll just keep that in mind when we work the next example. Let's now take a look at it. I've copied the threshold and our guess for the transconductance at the drain current that we're about to find here. Let's try to estimate the gain, but we'll start off with a DC analysis. 12 volts here is going to divide evenly across the two 1 mega ohm resistors. I already know that the gate voltage is just going to be 6 here. The source voltage here is just going to be about a threshold voltage below the gate voltage. Probably a little bit more than that, but this is usually a good estimate. We get 3.9 volts here, and we can then find our drain current. It's just our source voltage divided by that resistance, and indeed we find that it's 100 milliamps. Let's now find our drain voltage. It's just a little bit below 12 volts, so we'll use Ohm's law across the 50 ohm resistor. And we know 0.1 amps is flowing through it. We get 7 volts here at the drain. So we have a high voltage at the drain, a medium voltage at the gate, a lower voltage at the source, so everything should be fine here. This transistor ought to be in saturation. That's good. That's what we want. Now let's find the power consumption. The power consumption of the transistor involves current and voltage. So we have a voltage drop across the transistor itself and some current going through the transistor. So this is how you find how much power the transistor is dissipating or burning up on its own. We have 0.1 amps flowing through it. We have 7 volts at the drain and 3.9 volts at the source. We calculate 0.31 watts. That's okay because it's less than 370 milliwatts. Let's start off with our AC equivalent circuit. We have a signal and then a signal resistance of 1 kilo ohm. We then arrive at our gate. And let's assume that our capacitors are large. Our input impedance is just 1 mega ohm in parallel with 1 mega ohm, so we have 500 kilo ohms here. Let's put it in our AC equivalent circuit. Now we know this is a common source amplifier, and we can just remember that for common source amplifiers, the gain here is given by this resistance looking up from the drain, divided by all of the resistances looking down here from the source. That gives us 50 ohms here in the numerator. And for the denominator, we have a very large capacitance that bypasses the 39 ohms. So the only resistance we're left with is the little resistance due to the transconductance of the transistor. So we could imagine that this resistance here is 1 divided by Gm. So that ratio gets multiplied by our gate voltage. Finally, we have the output impedance of the circuit, which in this case is 50 ohms. And then we have, finally, our load. Let's call this our load voltage. And our goal is to find the load voltage divided by the signal voltage. So our net gain is given by 3 different components. First, we have an input voltage divider, then a gain segment. And if we plug in 1 divided by 0.2, we get 5, and then an output voltage divider. This works out to 0.998, and that's really typical of MOSFET circuits. You hardly have any problem over at the input side because we're allowed to use large resistors there to bias the gate. Our gain segment is only 10 here, so it's more modest compared to what we would expect with a bipolar transistor in a similar configuration. Finally, we have an output voltage divider here, which in this example is 0.995. So basically, our gain is about negative 9.9. I mentioned before that we might want to use a fudge factor because it's never usually quite that good, and we had a lot of estimates here, so we want to be super conservative. I simulated this circuit in LT Spice, and it gives a gain of minus 7.48. So there's always a little bit of uncertainty with the transconductance that you want to keep in mind. Don't count on the gain being as high as you calculate, but it gives a reasonably good estimate. Let's work one more example, and we're again going to take a look at the data sheet first. So let's use the same transistor, the 2N7002, and we can take note from the data sheet that our transconductance at 200 milliamps varies between 80 and maybe 320, and it says 320 is typical. In the last problem, we made a guess that if our drain current is 100 milliamps, then the transconductance drops to about 200 millisiemens. In the next problem, we're going to drop the drain current all the way down to 10 milliamps, so we need to come up with a new estimate here. 200 milliamps has quite a decent slope here. 100 milliamps would drop the slope by a certain factor, not quite a factor of 2, I suppose. But if we're way down here at the bottom of the curve, you can imagine that our slope is going to become even more shallow. These things are always difficult to estimate, but I imagine that we're going to have a factor of 10 difference or so. Let's just say that the transconductance might be something like 20 millisiemens. Anyway, we know it's going to be pretty small from the looks of these curves. What I'm trying to show you in working these successive examples is that if you have a lower drain current, you typically expect a lower transconductance. A lower transconductance then leads to lower gain overall. Let's again assume that we have some large capacitors scattered around this circuit, and we'll start off with a DC analysis. We have 12 volts at our power supply and an even voltage divider across these 1 mega ohm resistors. We're going to have 6 volts here at the gate. Our source voltage should be about a threshold below 6 volts. Our threshold here is 2.1 volts, so that gives us about 3.9 volts at the source. Our source current, or our DC source current, is going to pass fully through the 500 ohm resistor, so we can find it by just taking 3.9 and dividing it by that 500 ohms. That gives us 7.8 milliamps. We estimated our transconductance at 10 milliamps as about 20 millisiemens, so I think this estimate is probably reasonable for this source current. Let's now find our drain voltage, or our DC drain voltage. It's just going to be our power supply voltage minus the voltage drop across this 600 ohm resistor, or 7.32 volts. So we have 7.32 volts up here, 6 volts here, and 3.9 volts down here. This transistor should be in the saturation region. Good. Now let's proceed to the AC analysis. We have a signal over here. We then have a signal impedance of 1 kilo ohm, a large capacitor, and an input impedance of 500 kilo ohms, 1 meg in parallel with 1 meg. That brings us to our gate voltage. This is a common source amplifier, so I can remember that the gain is given by this resistance divided by all the resistances looking out from the source. I could just say 500 in parallel with 500, but because the drain current is so small, we might have a non-negligible resistance in the channel because the transconductance is so small. So let's include the little resistance right here in our calculation of the resistance in the denominator. That resistance, 1 over Gm, is going to be about 50 ohms. That makes it slightly non-negligible. So the 50 ohms is in series with these two 500s in parallel. If this had been a bipolar transistor, and you have anything other than a single large capacitor bypassing the emitter resistor, you can neglect the internal resistance to the transistor, but you can't always do that with MOSFETs. To complete the analysis here, we have an output impedance of 600 ohms, so let's draw that on our circuit. And finally, we have a load of 10 kilo ohms. Our overall gain is given by three different expressions. First, we have our input voltage divider, then we have our gain segment, and then we have our output voltage divider. Again, we notice that our input voltage divider is so close to 1 that we can almost always neglect it. Our gain segment here gives us a gain of -2. And then finally, our output voltage divider, in this case, is 0.94. Overall, the gain is -1.88. I simulated this, and the software told us that the gain here would be about -2. Here we calculated -1.88, so I think we were reasonably close to the simulated value. But if we were to actually build the circuit, I would expect a similar deviation between the performance of the circuit and what the simulator tells us to. Anyway, we're probably within a few tens of % of what the gain would actually be in a circuit. Overall, it's not easy to control the gain with common source amplifiers or with MOSFET circuits in general when you compare them to the case of bipolar transistors. A strategy, if you want to use MOSFETs though, is to just design circuits with really high gains and then use the concept of negative feedback in order to provide some control over those gains. In the next videos, we'll explore other MOSFET configurations so we can get some experience making other types of circuits.